Alright, so let's talk about simple harmonic motion, which is the final unit of AP Physics 1. If you're watching this next year, it's not, you still have one more unit, but at least for us it's one more unit, or the last unit. Let's just talk about what simple harmonic motion is. So simple harmonic motion is really the idea of repeated motion, so motion that kind of repeats itself. And the two big cases, and we're going to study these in depth, are going to be a pendulum, right, that swings back and forth, and then a spring, right, that kind of from that equilibrium position will oscillate back and forth. Not as a circle, but like just back and forth linearly. There are all sorts of different types of oscillation. Oscillation just describes repeated motion. I have my fan here. Oh, I didn't mean to turn that on. It oscillates, right? It goes back, forth, and then back again. Simple harmonic motion specifically, what kind of defines it, is the idea of a linear restoring force. So, for something like a spring, there is an equilibrium position, where if our spring was at equilibrium, there is no force exerted by the spring, because if we remember from Unit 4, force spring is going to equal negative kx, and we're going to talk about the negative. But if we double the distance that it's stretched, a linear restoring force just means, like the linear part just means that the force itself will double. So if the displacement doubles, the force itself doubles. Now, that means if I stretch it more and more, the force is going to get bigger and bigger. The restoring part just means that the force is opposite of the displacement. So take a look. If this is where x is equal to 0, right here would be a negative stretch, like a negative amplitude. We'll talk about amplitude. But I'm stretching it in the negative direction. So if I think about the forces, right, if we have the Fg and Fn, the force spring is going to be opposite of that. And then as I get to this territory, the force is going to be opposite of the positive displacement. So, it's going to point back to equilibrium. That's the key. The force always points back to equilibrium, right? And then the same thing kind of happens for a pendulum. So for a pendulum, there are actually a lot of forces. There's like force tension, force G, and then you can split up the components. What might be easier is just think about a linear restoring torque. So Fg right here, right? If this is our axis of rotation, then obviously Ft doesn't really produce any torque, right? It doesn't produce like any sort of torque because it's parallel with the the lever arm or the distance or whatever. The Fg will produce a torque, and you can imagine that torque will always point towards, the force will always, wait, let me think about this. I guess torque cannot point a certain way, but the Fg will always kind of point, it will always kind of be rotating it and swinging it back to equilibrium. That's kind of the key for a linear restoring force. So that's kind of what simple harmonic motion is all about. Right now we're going to focus on springs. Okay, so we talked about linear restoring force, we talked about linear restoring torque, and it repeats itself. Another key vocab word is amplitude, and we're going to start talking about mainly springs, and we'll apply it all back to pendulums. An amplitude is just how much you stretch it by. So you can imagine, if you think about energy, you think about forces, as we stretch it more and more and more and more, that initial stretch before we let go, more energy is going to be stored in the spring. There's going to be a larger spring force because of that equation right here. So that is just a vocab term to know. Period. Period is how long it takes to complete a whole cycle. So what do I mean by cycle? I mean how long does it take to get back to where you started? So a common mistake is people are like, okay, let me measure the period. We started here, and then it goes all the way here, and let me stop my recording. Well, it's not back to where it's been. So instead what you got to do is you got to go here, and then you got to record back, right? So it's in its original spot. Now it can get confusing, right? Because you can measure a period whenever. If you measure a period when it's moving right in the middle, then another mistake is that, oh, okay, it's going to go here, and then it's going to go back. Although it's returned to its original spot, the idea is that we want to reach every every place at least once. So it needs to reach the right amplitude, and then it needs to reach the left amplitude and reach all those spots, and then we will call that a period. So just some things to keep in mind. Frequency is a term, and if you take physics 2, you'll learn probably frequency more. I actually have no idea if you do. I don't know why I said that. But frequency is really the number of oscillations per second. So period, right? Cool. And then frequency is the number of oscillations in a given amount of time. So per second, number of oscillations per second. What's a way to calculate that? Well, we know that in a period amount of time, so in one period, the number of oscillations is 1. So you could do 1 over period. Or yeah, 1 over t is going to be your frequency. Because in one period, there's 1 oscillation. And this will have a unit of hertz, which is just the same as 1 over second. Okay, so that's just some terminology to be familiar with, because some problems might ask, hey, find the frequency, and then you use the period equation, but frequency is 1 over period, so you don't want to like mix these things up. So yeah, that's just some terminology. Springs, periods, right? A spring, when it's oscillating, will have a certain period, and there are a lot of things that could affect that period. So I think I'm just going to give the equation, and because I think if you remember that we went through the procedure of figuring it out, here's the equation. The period for a spring is going to equal 2 pi times the square root of the mass of this thing and over the spring constant of the spring. So mass of the block, spring constant of the spring. That wasn't clear. So, okay, there are some couple interesting things to keep in mind about this this equation. First of all, as we could see, increasing the mass. So if we were oscillating, right? If we increase the mass, well, not while it's oscillating. If the mass was bigger, the period would go up, right? So bigger mass means a greater period. A bigger k, so a bigger k, it has that inverse, square root relationship. A bigger k would cause the period to go down. Now let's kind of explain these things real quick. So if you have a greater mass, and I'm going to assume that everything else is the same. So in both scenarios, when we double the mass or whatever, same stretch, same amplitude, same spring constant, we're just seeing the effect on the period. So a greater mass means less acceleration. Now the reason for that, the reason why there's less acceleration when you have a greater mass is because it's the same force in both equations, right? Because force spring is equal to, we can do absolute values. Force spring is going to equal kx. So same x, same amplitude really. Same amplitude means same force spring, and that will ultimately result in less acceleration, because A is equal to force over m, right? A is equal to F net over m. Same F net, bigger m, less acceleration. And then it has to cover same distance, so same distance, right? It still has to go from one amplitude to another. It just has less acceleration, so you can imagine, even though the acceleration is not constant, so you can't use kinematics, right? Because acceleration here is 0, and we're going to talk about that. Still, same distance, less acceleration, you have a less average velocity, you're going to be moving slower, it's going to take more time. Now, for spring constant, it's very similar in terms of forces, right? This time you have a greater spring constant, that'll actually lead to more acceleration, because force spring equals kx. You have the same A, but you're going to have a bigger force by the spring, because your spring constant is bigger. It's a stronger spring. You're going to have a stronger force spring, and because of that, your acceleration is going to go up, because mass is same and then force is getting bigger. And same idea, more acceleration, same distance, greater average speed, you're going to be having a shorter period. Now, there's one variable that's not in this equation. Well, I guess there's many variables. Gravity is not in this equation. There's all sorts of variables not in this equation, but an important one that's not in this equation is amplitude. So amplitude is not in the equation. Now, the reason amplitude is not in the equation is, I'm not going to write this explanation down because I realize how much time that takes, but the reason amplitude is not in the equation is because when your amplitude is bigger or small, let's say it's bigger, right? When your amplitude is bigger, your force is exerting a greater, or your spring is exerting a greater force. So greater force because of force spring equals kx. So you're going to have more acceleration because your mass is the same, right, in both cases. So greater acceleration for a greater force. However, you have a greater spring, or sorry, you have a greater force spring, greater acceleration, but because you have a greater stretch, you have to cover more distance, right? You have a greater acceleration, sure, that's going to result in a greater top speed, but you're also having to travel more distance. So you're going to have a faster average speed, but you're still traveling more distance. It kind of all balances out. It's kind of like if I was racing Usain Bolt and he had to do 100 meters and I had like a weight attached to my leg, like who's going to win? Well, if I only have to run like 2 yards, then it's like I'm going really slow with less distance. It's going to balance out and we might tie because he's super fast, but he's running a long distance. That's kind of my analogy there. So that's why amplitude does not affect the period. Okay, I'm going to talk about pendulums now, and then I'm going to tie in graphs, and really, it's kind of the whole unit, just using this equation to figure out, like, maybe what's a spring constant, what is mass. There will be energy stuff. So I'll also touch on that and talk about how you can use energy in these problems. But the period of a pendulum is going to equal 2 pi times the square root of the length of the pendulum over the gravitational field strength. So, a couple things about this equation. There is length in the numerator. So that's suggesting that when your pendulum's longer, it's going to take more time to complete a period. And to explain that, what I would really say is, hey, when you have a longer length, you're going to have to travel more distance, right? It's going over my equation there, but you can see that arc length is much bigger, and if it's the same amplitude and the same theta, then for sure it's going to be a greater distance to cover. And your force gravity, right, the parallel component, or I guess the x component, however you want to say it, like that's the same force, because mass is same, everything is same. I don't know why I said everything is same. I mean, the angle's the same, so that component of gravity that's going to cause acceleration is still the same. I guess everything's causing acceleration, but still. So you're going to have the same acceleration, because same mass and same force, and greater distance, you can imagine. Overall, you're going to have a longer period. Now, if your gravitational field strength is stronger, you would see it has that inverse relationship, and that kind of makes sense, because if you have same length, same mass, same amplitude, but you just have a stronger gravitational field strength, your FG is going to be a lot stronger, so you're going to have more acceleration. But same distance, so you're going to have a shorter period. Same kind of reasoning there with acceleration and distance. Two kind of important variables are not in this equation. Well, I guess, once again, many variables aren't in this equation, but the two important ones are your amplitude and the mass. So this is where a lot of people kind of mix up, is that does mass affect does mass affect period or not? It depends what scenario you're talking about. For a pendulum, mass does not affect the period because of that kind of concept we've been honing in since kind of day one of forces. I don't know if it was actually day one of forces, but something that we've seen a lot is how Fg equals ma, right? Mg equals ma. The m's always cancel out. So if you have more mass, you have more inertia. You're kind of harder to accelerate. So you should have less acceleration, right? If you think about a is equal to f over m. But when we're talking about Fg, when you have more mass, even though your m gets bigger, so it's harder to accelerate, you get more force because Fg is proportional to your mass. More mass means more Fg. It essentially cancels out, right? Everything balances out, and you're going to end up with the same acceleration for the same period. And now, with amplitude, amplitude is a thing that for both of them don't affect. Kind of asterisk for the pendulum here, but for amplitude, right? If you have a larger amplitude, and I'm doing amplitude as like an angle, if I pull it back at a greater angle, then what's going to happen is I'm going to have more acceleration in the x direction. I'm going to have more acceleration in that like sort of tangential, direction, x direction, parallel direction, whatever. I'm gonna have more direction or more acceleration because that FGX, the component of FG is bigger. However, it's gonna be more distance, so it's more acceleration, but also more distance. Everything balances out, and the period should ideally be the same. Now, the truth is, a pendulum is not always an actual simple harmonic oscillator. Now, what does that even mean? What do you mean always a simple harmonic oscillator? As I talked about before, a simple harmonic oscillator, something that moves in simple harmonic motion, needs a linear restoring force, or at least a linear restoring torque or something like that, where doubling the amplitude doubles the torque or force. But a pendulum doesn't actually have that, because the torque is going to be Fg sine theta r, like for the length, I'll say L, but sine theta, that's not the same as theta. That's not proportional to theta, it's proportional to sine of theta. So if you double, if you know your trig identities, if you double the angle, you're not doubling this whole term. Sine 2 theta is not the same as 2 sine theta. So it's not actually a simple harmonic oscillator. It's only a simple harmonic oscillator for really small angles. Not really small, but like in small angles, because for really small angles, sine theta is actually approximately theta, and the way everything works out, you would have this equation. So don't need to worry about that too much on the test. It's always going to be like a small angle. It's always going to be an ideal pendulum, but just something to keep in mind. I guess if you're interested, that's how it really is. So that is really all of the unit in terms of new stuff. This is like all the new content. You still got to use energy, you still got to use conservation of energy, and you could have problems where you're trying to figure out like what is the speed at equilibrium if the period is if it starts with an amplitude of 2 meters and the period is 10 seconds or whatever, right? You want to figure out the speed at equilibrium. You would just do conservation of energy, E initial equals E final. At amplitude, all the energy is stored as U spring, and then at the equilibrium, there's no force, there's no elastic potential energy. All the energy is stored as kinetic energy. And then when you do 1/2 kx squared equals 1/2 mv squared, you're probably like, shoot, I don't know what k is. I know what x is because that's given in the problem, but what is k? Well, you know the period of a pendulum. You know it's 10 seconds just based on that problem. Plug that in here, and then you can figure out what k is, and then they'll give you the math obviously as well. And then you can figure out what the k is. You can figure out the energy problem, and you can figure out what v is. So yeah, not a lot of new stuff in terms of content. Really, let me just check what time. Yeah, I really hope it's not too long. 18 minutes. Okay, I'll end the video off going over the energy graphs and the position graphs and all that kind of stuff. We'll go over all the graphs because there's a couple I gotta talk about. I'll kind of make it quick. Nothing too crazy. So, the thing about these graphs is that they could be kind of like, like they could give you any kind of scenario and for simple harmonic motion, and it might be like, might not, like, for example, I'm going to start with position, right? If they give you position versus time, it might be cosine, right? Because it starts at an amplitude, and then it goes to a negative amplitude, so I'll say x versus time, and then it goes back to the positive amplitude position. So if you want to think about, well, what is this velocity versus time graph going to look like? If you're in calculus, you could do the derivatives, right? Derivative of cosine is negative sine, but obviously most of us are in calculus, just look at the slope. Slope is always velocity for position versus time. So I just say, hey, the slope here is 0, velocity is 0. Slope here is negative, velocity is negative. Slope here is 0, velocity is 0, and then you would just keep doing that, and hey, you get your curve there. Same thing for acceleration versus time. This is really not a new skill, right? I'm just saying, okay, well, acceleration is slope here, right? This is acceleration for the slope. So I'd say, well, the slope here is negative. Slope here is 0. Slope here is positive. Slope here is 0. And then you get your cosine. So, yeah, not this skill of looking at the slope and then making a new graph, not really new. That's just kinematics. But this time we're just seeing a new type of graph where it does like repeat itself, like a sinusoidal curve. So yeah, how do we know it's a cosine curve? Well, thanks to calculus, we can confirm that this would in fact be a cosine shape. So cool stuff there. And then if we're doing, let's say this is for a problem with a spring. This could also work for a, it could also work for a pendulum, right? Even though it's in 2 dimensions, we're just looking at 1 dimension. So everything would work out the same. If we're looking at a spring, right, and it's starting at the positive direction, we can imagine, what is this forced spring versus time going to look like? And now I'm going to do the same thing. I'm going to say, hey, remember, forced spring is always going to be negative k times the displacement. So whatever my displacement is, the forced spring is just going to be proportional to the opposite of that. If my displacement is positive, my force spring is going to be negative. When my displacement is 0 and it's at equilibrium, my force spring is going to be 0. So you can use that graph and then draw out your respective curve. It's going to be like some sort of sinusoidal curve. And once again, this could work for like FG tangential for pendulum, right? Like similar harmonic motion, everything kind of works out the same. And what we can do is now we can go over the energy ones. So for energy, kinetic energy versus time. What are we doing? U spring versus time. Then we're going to do TME over time. No outside forces, so mechanical energy is conserved. TME is going to be constant. Awesome. For U spring versus time, what we're going to say is, okay, well initially, this one you kind of have to think about. Initially, and we're doing one cycle. This is one cycle where it starts, goes to negative A, and then comes back. So initially, it's at stretch, so all the energy is going to be U spring. At this time, there's no stretch, so there's going to be no U spring. And then for here at this time, half the period, there's going to be more stretch. Same amount of stretch, in fact, because it's the same amplitude. And then we kind of repeat that, and then we will actually get sort of two, curves, I don't know what you call it. Like here we have like one curve, but this one you get two in one period. And you can get this all not by memorizing, just by looking at the other graphs. And hey, once you have U spring, and it's going to be a sine curve, there's not going to be any cusps or anything, it's just going to look like a sine cosine curve. And you can probably confirm the shape with calculus. Once you have U spring, total mechanical energy is conserved, so if U spring is at a maximum, your kinetic energy has to be 0. When U spring is 0, all the energy is kinetic energy. And you kind of can make your kinetic energy graph pretty simply. Okay, so yeah, those are kind of the graphs that you hopefully are comfortable with at this point. The last kind of graphs I want to go over is just some period versus certain variable graphs, right? Like what is the, how would you draw a graph, like period versus length or something like that? And my advice for that is, hey, just look at the equation. You get an equation sheet, so you don't even need to memorize the equation. You just gotta look at them and think about the shape. So if I ask, okay, sketch the period for the length of a pendulum. So period versus length. How does the length affect the period? Well, I would know it's square root, because pendulum is going to equal 2 pi square root L over G. And then obviously if you want to linearize it, we would want to square both sides. We have TP squared is going to equal 4 pi squared L over G. So to linearize it, we would need period squared. So that's kind of the graphs. For these graphs, you're just looking at the equation and thinking about how do I linearize it. That is like a skill from from all year. That's like a thing that hopefully you're comfortable with. If they ask you like, hey, what is going to be the period effect versus amplitude? Or in this case, for pendulum, the mass. If it's not in the variable, if it's not in the equation, sorry, if the variable is not in the equation, That means that no matter what your amplitude or mass is, it's going to have the same period. That's why we would draw a straight line, because that's telling us, hey, for this amplitude, this is the period. For this amplitude, it's the same exact period when you're plotting your points. So, yeah, not much to really note. And if you're like, hey, what's the slope of this? Just look at, like, okay, L is going to be our x, this is going to be our y, our m, and y equals mx plus b. There's no asymptote or y-intercept. Our slope is just going to be what's left over, 4 pi squared over g. And then I can just kind of move it over there. And that's our slope, and then you can figure out what g is based off that graph. And then you can do the same skills for period of a spring. You can like figure out, hey, t over m is this, right? This would be t squared over m. Mass, you know, this is now like for a pendulum, so it wouldn't work here, but then the amplitude would still be that flat horizontal line. So, yeah, that's all Unit 8. I kind of rushed at the end there because I kind of had some work to do, but hopefully this unit's not too bad, and it's not that much length, like it's not much on the AP test about this, so just, yeah, thank you for watching. Good luck. AP test is on Friday. I'm going to probably make some sort of video before then as well.